Beta emission. Objectives: to understand the radioactive process of beta emission, to study the properties of beta particles. You might have used papers of different thickness. You might be wondering how the thickness of these papers is controlled while manufacturing them. For this, a technique is used in which a radioactive element is placed on one side of a moving sheet of paper and a radiation detector on the other side. The radiation coming out of the radioactive substance passes through the paper sheet. It is found that if the thickness of the sheet increases, the count rate in the detector decreases and automatically the thickness of the sheet can be known. Because of good range of beta particles, beta emitters are suitable sources for monitoring the thickness of thin sheets. This beta emitter sample contains a number of radioactive atoms which decay randomly. Consider one of the undecayed atoms. It contains an unstable nucleus which eventually disintegrates by emitting beta particle along with a neutrino, and an atom of the different element is formed. We know that the stability of a nucleus depends on both the number of protons and the number of neutrons present in the nucleus. The periodic table mostly contains stable elements. For stable nucleus of every element, if we plot the graph of neutron number versus proton number, we get a stability curve which represents stable nuclei, whereas unstable nuclei of radioactive isotopes of all elements lie above and below the stability line. The elements having proton number less than 83 attain stability through beta decay. There are three types of beta decay processes: beta minus emission, beta plus emission, orbital electron capture. Let us see beta minus emission first. The elements lying above the stability line disintegrate by emitting beta minus particle or electron. Consider the parent nucleus of a radioactive isotope of platinum having 78 protons and 200 nucleons. During its beta minus decay, a neutron changes to a proton, an electron, and antineutrino. The electron is emitted as beta minus particle along with the antineutrino, and the proton remains in the nucleus. The daughter nucleus of gold thus formed has the neutron number decreased by 1 and the proton number increased by 1. But its nucleon number remains the same. Beta plus emission. Unstable nuclei lying below the stability line will attain stability by beta plus decay. To understand it, consider the parent nucleus of a radioactive isotope of thallium having 81 protons and 200 nucleons. During its beta plus decay, a proton is converted into a neutron and a positron. The positron is emitted as beta plus particle along with a neutrino, and the neutron remains in the nucleus. The daughter nucleus of Mercury thus formed has the proton number decreased by 1 and the neutron number increased by 1. But it still has the same nucleon number. Orbital electron capture. To understand it, consider the parent nucleus of a radioactive isotope of rubidium having 37 protons and 83 nucleons. During orbital electron capture, a radioactive nucleus of rubidium absorbs one of the atomic electrons, and as a result, a nuclear proton becomes a neutron emitting a neutrino. The daughter nucleus of krypton thus formed has the proton number decreased by 1 and neutron number increased by 1, but its nucleon number remains the same. Orbital electron capture is closely connected with beta plus emission. Heavy elements with Z greater than 83 disintegrate by positron emission or orbital electron capture or alpha emission. In the beta decay process, both charge and nucleon number are conserved. Beta particles in the above processes are ejected with high speed from the nucleus. Beta particles are deflected in electric and magnetic fields. Being smaller and more energetic than alpha particle, beta particles have greater range and hence greater penetration power than alpha particles in a medium. They easily go through a piece of paper, but most are stopped by 10 mm of wood, 3 mm of aluminium, or 0.1 mm of lead. Summary: in beta- emission, a radioactive nucleus, by lying above the stability curve, becomes stable by emitting electron. In beta+ emission, a radioactive nucleus lying below the stability curve becomes stable by emitting positron. During orbital electron capture, the nucleus absorbs one of the atomic electrons and becomes stable. Beta particles are emitted with high speed and are deflected by both electric and magnetic fields. Being more energetic, beta particles have more penetration power than alpha particles.